salts, which is just another name for ionic compounds, can also have an effect on the pH of a solution when dissolved in water. So the ions of the salt can behave as acids or bases. So the first case is we have ions from strong acids, such as Cl- from HCl, or nitrate from nitric acid, or cations from strong bases, such as K+ from KOH, or Na+ from NaOH. So when we have an ion coming from a strong acid or strong base, it has no effect on the pH because the attraction for H+ is very weak. Remember that strong acids produce very weak conjugate bases. So when we're dealing with salts and their ions, we'll have something, for example, we could have F-. Well, when we look at a table, we can see the Ka value for HF, hydrofluoric acid, but we don't know the Kb value of the F- ion. So we need a way to figure out the equilibrium constants for the ions from the original acid or base that they came from. So we can do this by looking at the equilibrium expressions for both the Ka of a weak acid and then the Kb of its conjugate base. And this also works for a weak base and its conjugate acid. So the general weak acid dissociation is Ha goes into H+ and A-. And then the general weak base equation, we have A-, it's taking in a proton from the water to form Ha, and then the water becomes the hydroxide ion. So if we write the equilibrium expressions for both of these, and then we multiply them, we notice that the A- and the Ha both cancel out, and all we have is the concentration of H+ times the concentration of hydroxide. And we know that is the equilibrium expression for the autoionization of water. So this is equal to Kw, 1 times 10 to the negative 14th at 25 degrees Celsius. So for any weak acid or base and its conjugate pair, we have Ka times Kb is always equal to Kw. So therefore, if we can look up, say, the Ka of hydrofluoric acid in a table, then we can divide Kw by the Ka and find the Kb for the F- ion. So the next case is that ions are the conjugate base of a weak acid. So, for example, F- from hydrofluoric acid. Hydrofluoric acid is a weak acid, so its conjugate base, F-, is relatively strong, stronger than water, as opposed to, strong acids produce very weak conjugate bases. So the conjugate bases will produce the basic solutions because they have that attraction for the H+ proton, and so they can steal this proton from the water. So we have a 0.3 molar solution of sodium fluoride. And if we look at a table, we know that the Ka for hydrofluoric acid, which is the acid where this ion comes from, is 7.2 times 10 to the negative 4th. So in our solution, the salt will dissolve, and so a major species are the Na+ ion, the F- ion, and water. And we know that Na+, since it comes from the strong base NaOH, it will have no effect on the pH. But since F- is from a weak acid, it will act as a base in this solution. So it will react with water to steal a proton. And when it steals that proton, the water will become the hydroxide ion. So here is the equilibrium expression And then we can find the Kb of the F minus ion by taking the Kw and dividing it by the Ka of the acid that it came from, hydrofluoric acid. So we find that the Kb of the F minus ion is 1.4 times 10 to the negative 11th, which is very small. So then we make the ice chart. We start with 0.3 molar F minus, and again they are all in a 1-to-1 ratio, so the F minus ion will decrease by some amount x to reach the equilibrium, while the HF and OH minus will increase by that same amount. So then we plug these in to our equilibrium expression, and since the Kb is small, we can ignore this minus x. So then we solve for x, and then whatever we get for x will just be the concentration of hydroxide. And then we take the negative log of this concentration of hydroxide. We'll get the POH, and then from there we can get the pH, since the pH and POH always add up to 14. So the other case is if we have a cation, that is the conjugate acid of a weak base, such as ammonium, NH4+, is the conjugate acid of the weak base, NH3. So these will produce acidic solutions since they have that extra proton. So we have 0.1 molar ammonium chloride, and from a table we can find the Kb for ammonia, which is the weak base that this ammonium ion comes from. So the major species in this solution are the ammonium ion, the chlorine ion, and water. And Cl- comes from the strong acid, hydrochloric acid, so it will have no effect on the pH. So the only thing that affects the pH to a large degree will be the ammonium ion. So it will dissociate into the proton and ammonia, and then we just make the ice chart, and again we can find the Ka for the ammonium ion by taking the Kw and dividing it by the Kb of ammonia, the weak base that it came from. So then we just solve for x, and that will be the concentration of the H+, and then we can solve for the pH. So in both of these examples, only one of the ions had an effect on the pH. The other ion came from either a strong acid or strong base. So if we have a case where both ions in a salt can have acidic or basic properties, we can't do the math to calculate the exact values of the pH. All we can do is make a prediction. So you compare the ions Ka and Kb values. For example, if you had ammonium fluoride, you take the Kb value of the fluoride ion and the Ka value of the ammonium ion, and you'd compare them. So in that case, the Ka of ammonium is 5.6 times 10 to the negative 10th, while the Kb of fluorine is 1.4 times 10 to the negative 11th. So the Ka of ammonium is larger, although not by much, to the Kb of fluorine. So we predict that the solution will be acidic. If the Kb of the ion is greater than the Ka of the other ion, it will be basic. And the last case is if the Ka of the acidic ion and the Kb of the basic ion are equal, then we have a neutral solution. So again, these are just rough predictions of what will happen. You can't really be sure.